Imagine you want to make toast. You put bread in a toaster, you set the timer, the toaster heats the bread. This is a simple kind of control. We call this an open-loop control system. It follows instructions. It does not check the result. It just does its job. For example, it doesn't check if the toast is perfectly brown. It just runs for the time you set. This system is straightforward and often less complex. An open-loop system works without feedback. Feedback is information about the output. Think about our toaster again. You choose a setting, perhaps medium brown. The toaster elements heat up for a preset duration. It doesn't actually look at the color of the toast. It doesn't know if you used thin bread or thick bread. It doesn't know if the bread was already a bit stale or very fresh. It simply completes its heating cycle based on your initial command. The outcome depends entirely on that initial setting. Now let's define it more formally. An open-loop control system is one where the control action is independent of the output. The system's output has no effect on the control action. This means there's no self-correction. If something changes, like the room temperature making the toaster heat differently, the system won't adjust. It's like giving someone directions and then not checking if they arrived safely or took a wrong turn. It's a one-way street for commands. So the toaster is a classic example. You decide how long it should run. The toaster runs for that specific time. It doesn't matter if the toast is burnt. It doesn't matter if it's still white. The toaster has done its job based on your input. Other examples include a simple clothes dryer running on a timer, or a microwave oven heating food for a set time. These systems are often cheaper to build. They are also simpler to maintain due to fewer components. Now let's think about a different kind of system. Imagine an air conditioner in your room. You set it to 22 degrees Celsius. The air conditioner has a sensor. This sensor checks the room temperature. If the room gets too warm, the AC works harder. If the room gets cool enough, the AC slows down or stops. This is a closed-loop control system. It uses feedback. The system checks the result and makes changes. A closed-loop control system, also known as a feedback control system, is quite different. It uses information about the actual output. This information is then fed back to the input. The system can then adjust its control action. Think of it like driving a car and keeping it in the lane. You constantly watch the road, which is the feedback, and adjust the steering wheel, which is the control action. This continuous monitoring and adjusting helps maintain the desired outcome, even if conditions change. It makes the system smarter and more adaptable. The key difference is that feedback loop. In our air conditioner example, the thermostat acts as the controller. It measures the current room temperature using a sensor. It compares this temperature to the temperature you set, the set point. If there's a difference, an error, the controller tells the air conditioning unit to cool more or less. This process repeats continuously. This ensures the room stays at your desired comfort level mostly. It's a more intelligent way to manage a system. So, closed-loop systems are designed to automatically achieve and maintain a desired condition. They do this by comparing the actual condition with the desired one. Then they apply corrective action. Besides an air conditioner, a home heating system with a thermostat is another great example. Cruise control in a car is also a closed-loop system. It maintains vehicle speed despite changes in road incline. These systems are generally more accurate and can handle disturbances. Within closed-loop systems, we often talk about two main types of operations. These are servo operations and regulatory operations. A servo operation or servo mechanism is when the main goal is to make the output follow a changing input. Think about a radar antenna trying to track a moving airplane. The desired position, the input, is constantly changing. The control system must make the antenna's actual position, the output, follow that change accurately. It's about following a target. Regulatory operations, on the other hand, aim to keep the output steady. They work to maintain a specific value despite any disturbances. Imagine your home thermostat again. You set it to 22 degrees Celsius. The system's job is to keep the room temperature at 22 degrees. It does this even if someone opens a window, which is a disturbance, or if the sun starts shining brightly into the room. The main goal here is to reject or minimize the effect of these disturbances. It's about maintaining stability. Let's look at how temperature is controlled in a process. This is often a closed-loop regulatory operation. You have a sensor like a thermometer or a thermocouple. This sensor measures the actual temperature of whatever you're trying to control, say, water in a tank. This measured temperature is then sent to a controller. The controller is the brain of the system. It compares the actual temperature to the desired temperature, which we call the set point. It calculates the difference or error. Based on this error, the controller decides what to do. It then sends a signal to a final control element. In temperature control, this is often a valve. This valve might control the flow of steam to heat the water, or it might control the flow of cold water to cool it down. If the water is too cold, the controller tells the valve to open more, letting in more steam. If it's too hot, it reduces the steam. This cycle of measuring, comparing, and adjusting keeps the temperature just right. To understand control loops better, engineers use block diagrams. A block diagram is a simple drawing. It shows the different parts of the system and how they are connected. Each block represents a component, like the sensor or the controller. Arrows show the direction of signals or information flow. It's like a map for the control system. It helps us see how everything works together. In a typical block diagram for a closed-loop system, you'll see several key parts. There's the set point, which is the desired value you want. There's a comparator, often shown as a circle, which subtracts the measured value from the set point to find the error. Then comes the controller block, which processes this error signal. After that is the process block, representing the system being controlled, like our water tank. Finally, there's the sensor block, measuring the output of the process and sending that signal back to the comparator. This completes the loop. Closed-loop systems can often operate in different modes. Two common modes are manual and automatic. In manual mode, a human operator takes direct control. Imagine the thermostat for your heating system isn't working right. You might bypass it and manually turn the furnace on or off. The operator becomes the decision maker, directly influencing the final control element, like the valve. In automatic mode, the system does its job without human intervention. The controller makes all the decisions. Our air conditioner, set to 22 degrees, works automatically. It senses the temperature and adjusts itself. This is usually the preferred mode for efficiency and consistency. The system continuously monitors the process and makes necessary adjustments. This keeps the process variable, like temperature or pressure, close to the desired set point. Finally, let's touch on two important characteristics of processes: process resistance and dead time. Process resistance is like how hard it is to change something. Imagine trying to fill a large tank with a very small pipe. It will take a long time and a lot of effort to raise the water level. This is high resistance. If you had a large pipe, the resistance would be low and the level would change quickly. Dead time is a delay in the system. It's the time between when a change is made and when the system starts to respond. Think about an old shower. You turn the hot water tap, but the water stays cold for a while. That delay before you feel the hot water is dead time. In a control system, dead time can make control difficult. The controller makes a change, but it doesn't see the effect immediately. Understanding all these terms, open loop, closed loop, servo, regulatory modes, resistance, and dead time, helps us appreciate the technology around us, from simple toasters to complex industrial processes.